We're going to basically review the process of completing the square with this monster right here. So if you look at this equation, it has no numbers in it. Okay? Yep. However, we can still solve for x. Okay? It won't be equal to a value, but it will be equal to an expression with a's, b's, and c's in it because that's what we have. So do you see here why we couldn't use factoring? Factoring is totally dependent on the numerical values, right? So without knowing them, it's not going to work. So what we're going to do is we're going to complete the square. So it's going to kind of review the process from yesterday in a really generic form and then hopefully reveal to you some things that you may or may not have known before. So when we're trying to solve by completing the square and we have a polynomial like this, we have ax squared plus bx plus c. What was kind of our process we went through yesterday if we had all those pieces? So we want to make a perfect square. Right now, we don't have numbers, so we don't know that it's a perfect square or not. So let's assume it's not, because we don't know, right? So what would we want to start with? What are some things we need to do, right? Good. So one thing that we did is we moved the constant over to the other side because we weren't sure that that's the constant that we wanted in order to complete the square. So especially when it's not a number, we don't know. So we move it over. Okay. What else did we have to do? I see Ray. He gave you guys the first step. Come on, people. Step it up. Okay. What else do we have to do? Kristen? Okay, so we want to divide b by 2 and square it. That's what I'm going to do next, but there's actually one thing I have to do before that, because this isn't for sure in the format that I need. Will? Just the a is an issue first, right? We have to make sure this is a coefficient of 1 here, and we don't know what a is. So we're going to divide everything by a. And then Kristen was exactly right in the fact that once we have it in this format, we want to take that middle term, divide it by 2, and square it to get that wonderful number at the end that's going to for sure make this a perfect square. So, again, you might not totally like it, but we can take b over a. And we can divide it by 2. Okay. Remember, that's just the same thing as b over a times 1/2, which is b over 2a. And then we're going to square it, okay? So the constant that I'm going to add to the end of this is going to be b squared over 4a squared, because that's what I would get when each of these numerator and denominator were squared. So this would be b squared over 4a squared. I can completely do that. I can add whatever I want to one side of the equation as long as I add it to the other side as well. Is everybody good with where we're at so far? We moved over the constant, divided by the coefficient, and did the little pattern we found for completing the square. Okay? Our purpose in completing the square is to make perfect squares for one of two reasons. Either because we want perfect squares, so we can just use square roots to solve it, or we want perfect squares because things are more clearly written in perfect squares when we're trying to use them, like the circles I mentioned yesterday, when we get to those, or also like using like vertex form of a quadratic. In those things, you need a perfect square. So every time that you guys complete the square, that should create a quadratic that can be factored as a perfect square. That's our entire goal in doing it, so it's supposed to work out that way. So in order for this to factor, if it is a perfect square, which if we follow the directions, this is a perfect square, the middle term will be made as long as the first and last term of the binomials are like the square roots of the things that we have here. So it would take x times x to make the x squared. And what would be the constant in here? Haley? Yeah, b over 2a. And do we want a plus or a minus between them? Plus, okay? Because we have that positive middle term. Now, on the other side, everything over there are constants, which if we were dealing with number values, notice there's no x's over here, right? Everything would be a number, and we wanted to combine that number into one thing. So we still want to do it, even though they're not numbers. So we're still going to make a common denominator. That was kind of one of our most annoying parts yesterday, right, to add together the fractions. But we're going to do that. So I have an a and a 4a squared. I'm going to multiply the a by 4a because 4a times a will make 4a squared, which is what I'm looking for. But then that means I need to multiply the numerator by 4a also. So on this right side, I can combine everything together in a fraction with a common denominator of 4a squared. And the stuff that would be in the numerator of the fraction is negative 4 times a times c plus b squared. It's pretty amazing. Okay. Next thing I want to do, okay, if our purpose was to solve, it was to get x alone. We did this work to make a perfect square because now we can solve by doing what? Yeah, Hunter's right. He's got the motion here. Square rooting, right? So I'm going to go ahead and square root both sides. I just write the answer up here. So on the left side, that gives me x plus b over 2a. I just got rid of the squared part. On the right side, I can't forget to include my plus or minus. And just like it did yesterday with the number values, taking the square root is a little bit ridiculous, but then not too crazy. The denominator works out really nice, right? The denominator is 4a squared, and I'm trying to take the square root of that. So what am I going to get? 2a. So my denominator is 2a. My numerator has a bunch of stuff going on. You might feel like you want to square root the b squared, but newsflash, you can't because it's being added with this other stuff over here. So we're going to leave all that stuff in the radical. Okay. And then to get x alone, what do I need to do? Yep, I need to subtract this fraction over here that's being added to x. So I'm going to go ahead and do that. And here's what I have. X is equal to negative b over 2a plus or minus this giant square root over 2a. And I'm going to rearrange the stuff in the square root a little bit because maybe then it will look more familiar. Instead of calling it negative 4ac plus b squared, I'm going to call it b squared minus 4ac. And these two fractions could be written as one thing if we write them like this. So there's the solution to this quadratic equation if I solve using the completing the square. What does that look like to you guys? The quadratic formula. So newsflash, okay? An old man didn't sit there dreaming up the quadratic formula on his own, okay? I like to make up my own versions of history. So I imagine that it got really annoying going through this process every single time that you wanted to solve a quadratic, right? And we were able to do this with generic letters because every time you solve it by completing the square, you do the same thing. You move the constant over, you get rid of the lead coefficient, you do this little process, and then you finish with square roots. So if you do this generically without numbers, surprise, you get the quadratic formula. So the quadratic formula is really completing the square. Totally is. Same thing. They just packaged it real nice for you so you didn't have to go through all the steps. You just got to plug all the numbers in at the end. So for the part that says to use completing the square, you need to use completing the square. Because I need you guys to be good at completing the square for some other things we're going to do later. I totally get that it might not be your method of choice to solve, but we need to get really used to using that process for some things we're going to rewrite later on in the course, okay? So for the homework. But after that, quizzes, tests, whatever, when it says solve, I will never force you to use completing the square. I will make you do one homework assignment where you are forced to use completing the square to make sure you get practice. But after that, I'll let it go, okay? Yes.
So if you do, force us to do completing the square for one of the homeworks, will you do it for one of the weekly reviews?
Maybe. I don't think there's any on there that say that, but maybe. Okay. I can't remember. Tell you what, I'm writing them all. I don't think one has had it so far. I'll make sure it doesn't say use completing the square. Okay. I make them, so I won't do that. Okay, are we good with this? Are you guys having some mathematical satisfaction? This is one of my most favorite things in the world. This is why I love teaching Algebra 2 a lot more than teaching Algebra 1, because I feel like in Algebra 1, someone gives us this, and we're like, yeah, whatever, giant formula. Some guy made a giant formula, and then we have to sit here and use it. And then in Algebra 2, I feel like you guys gain enough understanding to be like, wow, like, this is how I was. But I really love math, so you got to like, I was like, wow, like, it wasn't just a random formula. Some guy didn't just make us put these numbers together this way. Like, totally came from something else. And then I find that pretty amazing. But that's why I like Algebra 2. For me, this happened in Algebra 2. I was like, wow, look at how those things fit together. And then in Calculus, okay? And then in this class called Real Analysis that, like, if you go take a lot of math in college, you'll do that, where you, like, prove all the calculus stuff, okay? So pretty amazing. And then stop having hatred for completing the square, because if you didn't complete the square, you wouldn't have the quadratic formula, people, okay? All right? So if you love the quadratic formula, you have to open your heart a little bit to completing the square, okay? A little bit. All right, we're only going to do the numerical examples because we've done a lot of the application examples. We did a whole separate assignment on the application, so I don't want you guys to think I'm ignoring the word problems. We did them, right? You guys did an entire, your Skill 4 homework was all on applications. You didn't necessarily solve them using the quadratic formula. We let you use technology or whatever else. Some people use quadratic formula. Some people use technology. So for today, so that we have time to correct our quizzes at the end, we're not going to do the application problems up here. That doesn't mean applications aren't important. It means we already addressed it in a homework assignment. Does that make sense to everybody? Okay. And then if you want more practice with application problems, you know there's a couple extra in your note guide that you could return to and try if you want. So we're actually just going to have you guys try example 1. So go ahead and solve that using the quadratic formula. Okay.
Is 2 rad 11? Yeah, it's a simplified rad. Plus or minus. Oh, yeah, plus or minus.
All right. So do a quick check on if you plugged things into the right spot and if we're okay with getting here, and then I want to talk about the simplifying. So is everybody okay with having a 2 plus or minus the square root of 44 over 10 at this point? Okay. So when I say simplify the radicals, that means rad 44, because it's 44 and 44 is 4 times 11 and 4 is a perfect square, is not the most simplified version of that radical. The more simplified version of that radical would be 2 rad 11. And this then actually simplifies because both terms in the numerator and the denominator have a factor of 2. We can view this as this. Now, you guys have to be really careful. I don't know if you guys will have the same issue, but last year this was one of the things. I told you guys how last year my averages were lower than I expected and stuff. And this was one of the places where people really struggled, was like simplifying radicals or understanding this fraction, that this fraction is really 2 over 10 plus or minus 2 rad 11 over 10. So if you came across a different fraction, let's say this is not the answer to this problem. Let's say this was the problem. I had people doing like this, and then the answer was rad 11 over 5. Okay, so understand, can this 2 and 10 simplify? Sure. And then instead of 2 over 10, that number would be 1/5, but there would still remain a rad 11 over 10 because this is the denominator for both of these terms. The reason that you see it 5 here is because both of these had a factor of 2. So even if we separated it like this, we see both of these reducing to having a factor of 5. So just be really careful that you guys aren't making up kind of your own mathematical rules when you're going about simplifying, and that you really understand what the notation means when that fraction bar extends over everything, that that's a denominator for every term that's there, and that you're using it appropriately according to that definition. Really? No, either one of these is, sorry, for this answer it'd be a 5 underneath. But so I don't care whether you kept it as one fraction or it was 1/5 over and then plus or minus rad 11 over 5. I don't care if they're two separate values. I just don't want you guys thinking that this cancels this out and then all of a sudden this is gone, right? And or that this is 5, it didn't cancel it out from rad 11. You guys just have to be really careful with your simplifying.
So for that, would you just keep it at 2 plus or minus rad 11?
Yes. Yeah. Is that what you were asking? Yeah. Okay. So you can either split it up and simplify it if you're really feeling it, or you keep it together, but please don't assume like multiple people. 2, oh, this is now a 5. Then all of a sudden the 2 was gone. Like, what happened to the 2? Why is this a 5? It was also under the rad 11. Like, just be really careful with your simplifying process. Okay. It's not like people don't know the quadratic formula. The errors that we saw were mostly like foundational errors, not understanding how fractions simplify when they have multiple terms in them. Is this okay with everybody? Okay. So then the last thing we're going to talk about today is the discriminant. So the discriminant is a specific part of the quadratic formula. It's the part that determines the number of solutions that you have. So in the quadratic formula, Okay, so in the quadratic formula, a lot of times we get 2 answers, right? What part of the formula is making us have 2 answers? Okay, so plus or minus, as long as there's something after the plus or minus, right, means we add something to get one answer, and then we subtract something to get the second answer, and that's how we're able to get 2 answers. Can you get more than 2 answers to a quadratic? No. Okay, it can only cross the x-axis twice, right? Solutions are x-intercepts. 2 is the maximum amount of x-intercepts, so 2 is the maximum amount of solutions. What's the minimum amount of solutions? Matt? 0. Good. Okay, we could push that parabola up or down to where it doesn't cross the x-axis at all. Okay? We actually saw an instance yesterday when we were solving where we got no real solutions, right? Why did we get no real solutions yesterday when we were solving? Alyssa? Good. There was a negative inside of the radical. So this plus or minus can create 2 solutions, but not always. If there's a negative under the radical, it doesn't even matter that I have a plus or minus. There are no real solutions, right? If there's a positive underneath the radical, then I want to add that number and subtract that number, and I get my 2 solutions. Can we get 1 solution? Yes. Okay, I can picture a parabola hitting the x-axis 1 time, right? How would that happen algebraically with this formula when you were plugging in? How would you get 1 answer, right? Good. If inside the radical is 0, right? Because then you're adding 0 and subtracting 0, but that doesn't change the number. And then look, if it was 0, that doesn't matter. Look, negative b over 2a. Do you guys remember that? Okay, that finds the x-coordinate of our vertex. So it makes sense that when it's 0, you only have one thing, and it's the vertex that's sitting on the x-axis, okay? So what we're going to do is this. We're going to find the discriminant. So again, the discriminant is the piece of the quadratic formula that is finding our solutions for us. So it is just this calculation. No radical, not the rest of it. Because everything we just talked about was there would be 1 solution if there was a 0 underneath the radical. There would be no real solutions if there was a negative underneath the radical. There would be 2 real solutions if there was a positive underneath the radical. Every sentence we ended with underneath the radical. So to know the kinds of solutions or how many we have, we just have to know what kind of number is underneath the radical. So this is what's underneath the radical. It gets its own special name, okay? Because it's going to describe for us how many and what type of solutions. It's not the answers, but it just gives us a general idea of what's happening with one quick calculation, okay? So we're going to split up the work. I will do the first one, okay? We're going to have that side of the room do the second one, so these 3 groups along that wall, okay? You guys are going to use this equation and find the discriminant. Middle groups, you guys are going to use this equation to find the discriminant. And this side of the room, you guys are going to use the last equation and find the discriminant, okay? So go ahead and quickly calculate the discriminant. It's just a number value by doing b squared minus 4ac. I wrote mine up from last period so I can cheat. And then just check with one other person that you're right, and then just call me over, let me know, and I'll go write it up. Yes. You guys got 0. Perfect. What'd you guys get, Elin? Negative 23. And Lydia on this side. 25? 25? All right. So 129 was my discriminant. What's my number of solutions? 2. 25 is my discriminant. What's my number of solutions? 2. If 0 is my discriminant, what's my number of solutions? And if negative 23 is my discriminant?
0.
Well, I'm going to be a little more specific and say no real solutions. You guys have a surprise coming your way, remember? Don't spoil the surprise. So, okay, so let's think about this. We're going to make a sketch. We are in no way are putting these parabolas in the right place. We just want to know with these quick pieces of information things that we should be able to tell. So with a discriminant of 129, I know there's 2 solutions. I know this parabola faces downward. I really have no idea what it looks like, but it should be something like this. It should cross the x-axis twice, right? Just putting together like what 2 solutions means graphically, okay? This one also has 2 solutions, right? But this parabola is concave up, so it's going to look something like this. This parabola has 1 solution. It's concave up. So it has to hit the x-axis right at the vertex. I'm trying really hard, but my pen is like not lined up. So there we go. Okay. And then this last one is a concave up parabola with no solutions, no real solutions. So this is something where it sits above the axis. Okay? Just a connection between solutions and what that means about x-intercepts. Okay? Those in no way are exact graphs at all. Okay? All right. The last thing we want to fill in is the types of solutions. So if you know you have them, what kind of numbers are they? Okay? So let's start with these ones. Both of these have 2 solutions. However, one of these would be much nicer for me to go and calculate in the quadratic formula, and I feel much more comfortable with than the other. Which number would you rather see underneath the radical in the quadratic formula? Yeah, 25, right? The reason we like 25 is because we know its square root. It's a perfect square, okay? And its square root would be 5. That means you would have no radical portion left when you were calculating your solutions, which means not only do you have these 2 real solutions, they're real because they cross the x-axis, but they are also rational. Meaning, worst case scenario, you get a fraction, but you're not getting a never-ending, non-repeating decimal. Okay? However, if you put 129 underneath the radical, anybody, what's the square root of 129? So it's going to be some crazy number, right? Something between 11 and 12, but it's going to be a never-ending, non-repeating decimal. Thank you. So this is also real. It does cross the axis. However, it's a much more difficult number to deal with because it's not rational. It's not something we can see as a fraction. It's irrational. What about our 1 solution? Is it going to be real?
Yes.
Yeah. Okay, if we're getting it and it's crossing the axis, we're getting a real number, the numbers that we know. Is it going to be rational then or irrational? Rational. If 0 is underneath the radical, am I going to have a radical portion left there making a never-ending, non-repeating decimal? No. So this will also be rational. When you have no real solutions, you guys have something called complex solutions. Okay, so the complex number system adds a new group onto the real number system. We'll talk about this next week. So complex numbers have the real numbers within them, but can also have this other part that we call imaginary. And we'll talk about that. Okay? All right. Are we okay with this? So expectation. Can I change this? Yeah? Any objections? Are we sure? All right, so expectation, again, we're not going to do the application problem right now because we did a whole separate assignment on applications. So let's just quickly look at example 3. If we have negative x squared plus 14x And we bring the 49 to the same side so we can clearly see our A, B, and C values. And it just says the number and types of solutions. I don't need to actually go find them then. I just need to do the B squared minus 4AC, the discriminant, to know what's happening. So B squared minus 4 times A times C. So 14 squared is 196. Okay. And 49 times 4 is 196. And a negative times a negative times a negative is negative. So my discriminant is 0. So interpret that for me. Good. One real, and we can even get more specific. It's real and rational. If you can say it's real, you can either divide it up into being rational or irrational. Okay? So this is one real rational solution. And then you could have a little picture of this quadratic in your head facing whatever way with the vertex on the x-axis, like understanding there's only one x-intercept. Okay? Are we all right with quadratic formula and this really special part of it called the discriminant and kind of what it tells you about? All right with everybody? And do you now feel